Hey there, Mr. Sutton here with the AB Calculus 4-4 Extra Practice Number 3 solutions on concavity. To find intervals of concavity for this rational function, we need to find the second derivative and analyze the sign behavior of that. So first derivative, we're going to need the quotient rule. That's going to be, let's see, box and ribbon time. We're doing u prime v minus uv prime over v squared. So we have x as our numerator, and x plus 3 is our denominator. Derivatives of those are going to be 1 and 1, so that works out nicely. So now putting this all in my big fraction, we've got x plus 3 minus x, using the ribbon here, minus x, all over x plus 3 squared. And since I'm going to take another derivative in a sec, let me simplify this. So this is, the x's can cancel. This is really 3 over x plus 3 squared. To make taking this derivative easier, I'm going to rewrite this as 3 times this stuff to the negative 2 power. And now I don't need the quotient rule at all. I can just use the chain rule. So multiplying now by negative 2, that's going to be negative 6 x plus 3 to the negative 3rd power. And I don't really need the chain rule. I mean, the derivative of x plus 3 is just 1, so that doesn't matter. I am going to rewrite this in fraction form, though. Negative 6 over x plus 3 quantity cubed. Just because that's going to make it easier to analyze the sign behavior and all the rest of it. All right, so for critical values, I need to figure out where this thing is either 0 or undefined. Well, it can't equal 0 because we have a constant in the numerator, but we can be undefined if x has a value of negative 3. That would zero out the denominator. So that gives us a critical value to put on our f double prime number line and do a little sign analysis around. Testing out a number less than negative 3, like negative 4, that's going to make the stuff inside this parentheses negative. Cubing it keeps it negative, but then the whole fraction is negated, so this all becomes positive. And then a number bigger than negative 3, let's use 0. So that gives me a positive down here, positive up here, but again, the whole fraction gets negated, so overall that's a negative result. Since f double prime is positive in this first interval, f is going to be concave up from negative infinity to negative 3. And since f double prime is negative over here, f is going to be concave down from negative 3 to positive infinity. To find intervals of concavity on this polynomial, I'm going to need to analyze the second derivative. So first derivative is going to be negative 3x squared plus 6x, and that negative 2 is going away. Second derivative, now we've got negative 6x plus 6. And I'm going to set this equal to 0 and solve for critical values. If I subtract 6 and divide by negative 6, my only critical value is at x equals 1. So I'm putting that on my f double prime number line here for some sign analysis. To the left of 1, let's try out 0. And I'm going to test it out in this f double prime equation here. So if I plug 0 in for x, that just zeroes out this first term, leaving us with 6, which is positive. And something bigger than 1, let's use 2. Negative 6 times 2 plus 6, that's going to come out negative. Since f double prime is positive until we get to 1, that means f is concave up from negative infinity to 1. And since f double prime is negative after 1, f is therefore concave down from 1 to positive infinity. To figure out intervals of concavity for this quartic polynomial, we need to analyze the sign of the second derivative, but let's start with the first derivative, which is 4x cubed minus 12x plus 2. And let's go one more derivative, so that's going to be 12x squared minus 12. So now I need to get critical values of this by setting it equal to 0 and solving. If I add 12 and divide by 12, we have x squared equals 1. And then x is going to be plus or minus 1 if you square root both sides of that equation. So our two critical values, which we can put on our f double prime number line here, are negative 1 and positive 1. So let me test out a number that's less than negative 1, and I'll plug it into this f double prime expression here. So let's test out negative 2. That's going to be 12 times 4 minus 12, which is a positive number. Now something between these critical values, let's use 0. That'll be just 0 minus 12, which is negative. And something bigger than positive 1, like positive 2. That again gives us 12 times 4 minus 12, which is again positive. Since f double prime is positive on these outer intervals, that means f is concave up from negative infinity to negative 1. and from 1 to positive infinity. Since f double prime is negative between our critical values, f is concave down from -1 to +1. For this problem, I want to know about the concavity of this function on various intervals. So let me start by taking two derivatives of this, because I need the second derivative to answer that question. First derivative, we're going to use a chain rule. This is going to be 1/2 times all of this stuff to the -1/2 times a tail of -7. So that's going to end up being -7/2 times all this to the -1/2. No, one more derivative now. We're going to have -1/2 times 7/2, -7/2, times another tail of -7. So let's do this in steps here. -7/2 times -1/2, that's going to be 1/4. Multiplying that by -7, we get back to -49/4. And the new exponent is going to be the -3/2 power. All right, so let me clean this up a little bit and put this in a form that it's easier to do analysis in terms of what makes it 0, what makes it undefined. So I'll rewrite this as a fraction with a radical. In my numerator, I'm going to have a 49. In my denominator, I've got a 4, and then I've got the square root of all this stuff cubed, like so. And the whole fraction is still going to be negative. So in terms of what makes this 0, well, nothing does, because you have a constant in the numerator. However, we can make this undefined by making the x value down here 5, because -35 and 35 would give us 0. But it actually is worse than that, because the square root, you're not allowed to square root negative numbers. So really, any x value that is 5 or greater than 5 is going to give us unhappiness in the denominator here. So this one is going to be undefined for x greater than or equal to 5. So we're only going to consider then x values that are less than 5. Now for x values that are less than 5, the square root can only give you back positive numbers, at least if you give it something it can actually square root. So we're guaranteed this whole denominator is going to be positive for any x values that are less than 5. Numerator is already positive. The whole fraction then is always going to be negative. So we see here that f double prime for x less than 5, f double prime is always going to be less than 0. Therefore, this function, the f function, is not going to be concave up anywhere because it's never a positive f double prime. And we are going to be concave down for x less than 5, for -infinity to 5. To figure out concavity for this polynomial, I need the second derivative. So first derivative, we've got 3x squared minus 6x plus 4. Second derivative, using the power rule one more time, that'll be 6x minus 6. And now I need critical values in sign analysis. So setting this equal to 0, adding 6, dividing by 6, we see that x equals 1. Let me put that on my f double prime number line to analyze the signs around it now. So let me test out a number less than 1, like 0. Plugging that into my f double prime function here, that's going to be 0 minus 6, which is a negative. And if I test something bigger than 1, like 2, that'll be 12 minus 6, which is positive. Since f double prime is positive on the right side interval here, that means that f is going to be concave up from 1 to infinity. And since f double prime is negative back here, that means f is concave down from -infinity to +1. To figure out concavity for this quintic polynomial, I need to take a look at the second derivative. First derivative is 5x to the 4th minus 6x squared. Second derivative then, again using the power rule, we've got 20x cubed minus 12x. And I'm just going to set that equal to 0 and find some critical values now because I need to do some sign analysis. I can take out a 4x out of all this. That'll leave me with 5x squared minus 3. And then I see that this is going to get zeroed out if x is 0. Or for the stuff in here, if I add 3, divide by 5, and square root at plus or minus radical 3 over 5. Let me put all that on my f double prime number line now. So I have negative root 3 over 5, 0, and positive root 3 over 5. And let me do some sign analysis. So a number to the left here, this number inside is less than 1. So the square root of something less than 1 is also less than 1 in terms of absolute value. So that means -1 is to the left of this. So let's use that. So I'm going to use this factored version of f double prime. So plugging -1 into this, that's going to give me a negative outside. Inside, 5 minus 3 is a positive, so negative times a positive is a negative. And now I need something between this and 0. So I'm not really sure about some nice numbers to plug in that are in between here. It seems like splitting hairs to get in between this negative radical and 0. I'm going to be safe and use negative radical 2 over 5. It's not the prettiest looking number, but it'll have to do. So plugging that into my original, or my f double prime equation, clearly we are negative outside. Inside, if I square this, I'm going to get 2/5. So that would give me, let's see, 2 minus 3, which would be a negative. Negative gives me a positive. And then I'll use the same trick over here. I'll use positive root 2 over 5. So that's a positive outside now. We still have 2 minus 3 inside for a negative there. So that's a negative overall result. And I'll use 1 for the far right interval. That's a positive times a positive, which is positive. Now, since my f double prime is positive in the second and fourth intervals, f is going to be concave up from negative root 3 over 5 to 0, and also from positive root 3 over 5 to infinity. And since f double prime is negative in the first and third intervals, f is going to be concave down from negative infinity to negative root 3 over 5, and from 0 to positive root 3 over 5.